Okay. So before we really get going, um, I wanted to give you guys some more details on the exam, the third exam that we're going to have. So it's going to be next week. It's going to be set up like a real take-home exam, like it would be if you actually would take it home rather than in class. So what that means is that I'm going to be posting the exam on Tuesday, and it's going to be due on Friday. So you'll have a good chunk of time. Um, there's um, there won't be any homework due next Thursday. I'm going to put a small assignment on functions that'll be due on Tuesday, just to give you a little bit of practice. And I really do mean small. It'll be the kind that you could reasonably do over the weekend and will serve as a good studying. So the exam is going to be covering material um, from when we started to what we covered today. So that's relations and then the sort of beginning of functions that we're talking about today. Um, and I'm going to be putting up a lot of material. So I'm going to be putting together a kind of practice exam / review. So those will show up on Canvas. I'm going to pick a time to do a review session. It'll be recorded, so if you can't make it, don't worry about it. You'll be able to see it. And so that'll happen, I think, Monday. And during the exam period, you are allowed to look at your notes, the textbook, the videos that have gone up, your homeworks. You can also talk to me. We can talk over email or have some office hour time where you can get help working on these problems. So that's what to expect. And if there are any other clarifying questions, I'll be happy to answer those. But for now, I want to get going onto the new or the material of the day. And since this exam is a take-home exam, we will have normally scheduled classes both days next week. Okay. Let's do this. Okay. So what we've been, or the new, not really new, but the object that we're going to be focusing on today and that we started talking about last time is a function. So you've encountered functions a lot, but the way that we're going to be proving properties about them is that we're going to be thinking about functions as particular kinds of relations. So a function is a set of ordered pairs such that for any first coordinate from the first set A, there is exactly one second coordinate B, so the pair AB is in the function. So that means F is a set of ordered pairs, and if you appear as a first coordinate, you only appear once. And so that matches the way that we kind of think about functions as saying you have an element A and you are sending that or mapping that, or the function takes that A as an input and outputs something from B. So if you are a valid input, then there's only one output that corresponds to you, and that's this pair AB. And so we use this common functional notation. Every A, if you are in the domain, if you are a valid first coordinate, then there's only one B which shows up in a pair with you. That B is totally determined by the function you're talking about and the A serving as the first coordinate. So we call that f of A. And if we're talking about the function is a set of ordered pairs, and it's the ordered pairs that look like this. Some first coordinate from the first set A, and then the corresponding output, which is the only second coordinate that gets paired with A. And the sort of balance that we're striking in talking about this now is that we have an idea of how functions behave. But most of the other times we talk about functions, it's been with some kind of formula, a formula that says, given an input, here's the output that gets paired with it. And that formula really tells you what pairs are in the graph or are in the function, which we can kind of think of visually as the graph. Plot these ordered pairs in the XY plane if your function is from a set of real numbers to other into the real numbers, you can actually draw a picture of this. But when we get theorems like this one we proved last time, saying that f equals g if for every a in A, f of a equals f of g, we went through this last time, but the way that we are sort of understanding this is this left statement is saying f and g are relations, meaning they're sets of ordered pairs. And if those sets of ordered pairs are the same, then we can just, that is equivalent to saying for every A from the first set, the second coordinates that the two functions give you, or the outputs the two functions give you, are the same. And this is more the way that you would think about functions being equal, is they always do the same thing. Even if their formulas are a little bit different, they always give you the same outputs. So a lot of the statements that we're proving are from the point of view of if we want to prove things about them, a function is really a special kind of relation, so we have to think about it in terms of the ordered pairs that make up that relation. And as we also talked about last time, we have these other concepts which we talked about with relations, but are actually much more familiar when we talk about them with functions. So this notation here, this, if you write this down, you mean f is a function from A to B, which means f is a relation from A to B, so it satisfies this functional property. Every element of A is paired with exactly one element of B when you look at all the ordered pairs. And so we talked about the domain. Because of how this is defined, if you write this bunch of symbols down, the domain is all of A, because we're saying every element of A has a corresponding element of B, which means every element of A appears as a first coordinate. And the range similarly is all of the second coordinates. All the second coordinates look like the function value for some input. And so if we're talking about the range, you could say this is an indexed set where the index is A, and how we know what's in the set is take an element of A and find the function that corresponds to it, or find the element which corresponds to it under the function. So in a couple examples we saw last time, this example is really to say this V defined by this formula is a function from R to R. That isn't the way that we're using this notation because R isn't the domain. 0 isn't a valid input. There's nothing that we pair with it. So if we want to say that this is a function, we really have to specify this is the domain we're talking about, and it goes into the set of real numbers. Talking about the domain, another kind of thing that can come up is, in this example, we have the same formula, x squared plus x, but they are different functions because they have different domains here. So for these functions defined by a formula, you get to specify what the allowable domain is. In pre-calculus, you often think of the domain as the largest possible set of inputs, but now when we talk about a function, we need to be really explicitly saying what the domain is. So it's not just a formula. A function is going to be what are the allowable inputs and what are how do you find the outputs of those if you're going to specify it by a formula. And with this example in mind, and I fixed a little typo here, what is not a controversial statement is x squared plus x is a function of reals. If we shrink the domain, that is still a function from the natural numbers to reals. So here you're only allowing whole number inputs. And these two functions, it's the same formula, so they do the same thing when you put in a natural number. So f of 1 and g of 1 are identical. F of 1, oh, wait, I wasn't expecting that. Equals 1. So even though these are two different functions with two different domains, they're defined by the same formula. So as long as you're using an input where they both are defined, using an input in the domain of both of them, they agree, which is what you would expect. It's the same formula. Of course, they're going to agree. But what we want to, or what we'll prove next, is this kind of general construction saying start with a formula on, or start with a function from a set A to B and look at just a subset of A. Then if we form this restriction, so this is read F restricted to C, which is saying take your function, but only look at ordered pairs where the first coordinate comes from C. So this is also a function from C to B, and the function value at a point C for the original function is the same as the function value at C for our restricted function. So what's happening is the same move we're making here. You have a function defined on a large set, you cut down the domain, but otherwise you're thinking about the same ordered pairs. Just you're shrinking what are the allowable first coordinates. And in this proof, we can't use that the function has a formula. And we can't just say, well, you're using the same formula, so of course it's a function and of course it does the same thing. Because thinking of functions as formulas is a very restrictive way of thinking about functions. A function is just any correspondence that satisfies this functional property. And through most of your life, you've seen it represented as formulas, but in a lot of cases, they aren't. If you've taken Calculus 2, you've seen that functions can be represented as power series. Um, and that's not a formula, but it's a way of saying you have an input and there's a corresponding output. If you're taking Calc 2 now, we're getting there. But functions are a lot more complicated than just the sort of basic formulas that you've seen. So when we want to prove a statement, we can't use that as a formula. The only thing we can use is that F is a set of ordered pairs that has a particular property. And we'll want to show that this is a set of ordered pairs, which also has that particular property, and they're related in some way. So as we're going through a lot of the proofs that we're doing in this section, a lot of insight can be gained by thinking about particular examples that arise as formulas, but the proofs need to be much more general, just talking about sets of ordered pairs. So to actually prove this, we need to get into what ordered pairs are we talking about and how do we check the properties that we have. So the first step is here we have this definition. And so what we know is that F restricted to C, it is some set of ordered pairs. F is a bunch of ordered pairs, C times B is a bunch of ordered pairs, and we're intersecting them so we get some smaller thing of ordered pairs. So it's the right type of object to be a function, but to be a function, there were really these two properties you need to have. Or the functional property, there are really two aspects of it. First is that every member of C appears as a first coordinate. So every member of C has to appear in a first coordinate of one of the pairs in here. The second part is the uniqueness that says every member of C appears as a first coordinate, but it can only appear once. So there are two aspects of proving that something's a function, and we'll have to walk through both of those. And the key step in this proof is that F is a function. So F has these properties, and we are trying to say that this, take F and intersect it with this set, still has those properties. So what does a proof look like? So the proof of something being a function, the existence part says, let little c be an element of capital C. So here we're taking something from our first set and wanting to show it is part of an ordered pair in this function, or this set, this relation which we want to prove as a function. So what we can say is we pick a little c in C, but we assumed that capital C was a subset of A. So this little c is an element of A, and now we're in the larger set where our original function applies. So if little c is an element of A, then it appears as the first coordinate of a pair in this function. So that's good because we want to show that, or we want to talk about this intersection here. And we know that here's a pair which is in F. But we can also say for this pair, C, F of C, that it comes from the product of C and B. Because little c is in capital C, F of C is a member of the range, which is an element of B. So this means that this pair, CF of C is in F, and CF of C is in C times B. So it is in their, well, So by definition, if it's in both of them, it's in their intersection, which is what we're calling this F restricted to C. So this proof is just sort of following this C around, but we need to know where we're trying to get to and what we're actually trying, and how we use the pieces that we have. So we need to, given this C, we need to find some pair that has this C in a first coordinate, and the pair comes from this restriction. And so that's where we do end up. Because we found a pair with C in F, and we found that same pair with C in C times B. So that proves that every member of C appears in one pair with something in B, but now we need to prove that it can only appear in one. And the way that this is often done is assume that it appears in two and show that they're actually the same. So this, when we introduced functions before, no, sorry, I'm thinking about something else. Never mind. Right. So proving this is unique means that if you write down it being in two different pairs, they actually have to, you actually aren't talking about different pairs, you've just kind of named the same thing twice. So we assume that C has two outputs, call them B1 and B2, for two potentially different objects that it could be related to by this relation is all we know. But what we can say is that if these pairs are in this restriction, well, the restriction is the intersection of F intersection another set. So that means if they're in this set, which is the intersection, it's in each of the things that are intersected to make up F restricted to C. So these pairs are also in the function F. F is a set of ordered pairs, so, and includes F restricted to C as a subset, because this restriction is an intersection. So these pairs also live in the set of ordered pairs of F. But F is a function, and how you use the fact that F is a function, at least for this half, says you have two pairs with the same first coordinate in your function. The only way for that to happen is if these second coordinates are actually equal. You can't have two different second coordinates that get paired with a single first coordinate. So this B1 actually has to equal B2. And that's really what we wanted in the first place. We wanted to say, if you name two second coordinates to pair with C, they actually have to be equal. They can't really be different second coordinates. And that proves that this is a function. This set of ordered pairs we can write down has this functional property where every C is related to something in B and everything in C is related to only one thing in B. For this last part, we actually proved this along the way. We just need to identify that we really did prove it. So for the second claim, it's a for all statement. So let C be an element of C. And in this existence part, we said, take any C, like this one, and this ordered pair is in this function here. And so that means that if you take C and find its input or find its output that the restriction gives you, that is the same output as what happens if you put C into the original function. So this f of C is some member of B. That is the second coordinate that gets paired with it in F, and that is also the second coordinate that gets paired with it in the restriction. So that's the proof, which matches what we expect. If you take a function and just apply it on a smaller set, if you shrink its domain, it's still a function, just it's a function on that smaller set. And on that smaller set, it behaves like it did, like the original function did. You get the same output. Questions about this proof? So this proof is kind of good construction to see. We can take functions and shrink their domains, and we still get a function on that smaller set. But it also is to indicate the types of moves that we're going to be using. First, getting used to tracking these ordered pairs as they go around, but also indicating that we're going to be making assertions that something is a function. And that statement requires proof, and the proof will look like these two parts. Your object, well, it has to be a set of ordered pairs. It has to be some relation first. But then you're saying for every first coordinate or every potential first coordinate really does show up, and it only shows up once. So these two halves of this functional property are going to show up every time we want to prove something's a function. Okay. So composition of functions is again a idea which appears sometime in the middle of pre-calculus when you're talking about functions. But how we're going to look at it is we talked about composition of relations, and a function is a special kind of relation. So what we're going to see is if we prove statements about composition, thinking of a function as a special kind of relation, that matches with the intuition we have from pre-calculus of how composition works. So the intuitive way of how composition works is you have two functions, f goes from a to b, g goes from b to c, and you compose them, which says take something in a, send it to b, and then send that on to c, and that two-step process is the composition. But the way that we're going to prove things about it is that f and g are relations, and we talked about the composition of relations. And from how that was defined, we're going to prove properties of what if you happen to know that these are both functions, what can you say about the what you get when you compose them? So the relation says something in A is related to something in C if there's some B. So A is related to that B, and B is related to that B is related to the C that you started with. So as our first fact that we really need to prove is suppose that we have two functions, f is a function from a to b, and g is a function from b to c. So we have this picture. Then g composed with f is a function from a to c. That's what this is saying. So we need to prove that this is some relation. It's actually a function from a to c. And then beyond knowing that it's a function, we want to think about how do we compute values of the function? How do we find outputs for some given input? And we'll want to prove that this formula that you've seen before, if you apply the composition to some input A, that says take A and find its corresponding output under F, take that and find its corresponding output under G. So the statement is not new. It's how you've seen composition work. And really, this is the way that it was defined before. But now we're thinking, this is a relation, this is a relation, this is another relation. I want to prove this relation has a certain property. And once I prove it's a function, I want to prove this fact about how we actually get the second coordinates for a given first coordinate. So first up, showing that this is a function. Well, before we do anything, it is good to at least mentally recognize that this is a set of ordered pairs in A times C. So G composed with F is a subset of A times C. So it is a set of ordered pairs. The coordinates come from the right places to potentially be a function from A to C, but we need to prove that every member of A appears as a first coordinate in here, and it only appears as a first coordinate once. So we have the same pair of statements or types of statements that we need to prove that we did in the last case. We need to prove first that every A, it is in an ordered pair, and then we have to prove that it's in at most one. And where these ordered pairs are going to come from is we're going to be using the definition of this as a relation. So if we are, so this as a relation, but also we know that we have these two functions here. So start with an element of A, we need to show that it appears in an ordered pair in this relation. So since F is a function and this is an element of A, F pairs A with some member B from the set B. And then G is a function from B to C, so it pairs this B with some third element C in C. So as far as what pairs there are, the pair AB is in F, and the pair BC is in G. And this setup is exactly what has to happen for the ordered pair AC to be in the composition. These two are related in this relation because there's some third element B which connects them by the two individual relations. So A is related to B by F, B is related to C by G, so A is related to C by their composition. Then for uniqueness, like we did in the proof on the top half of this page, we say take an element A of A and assume it appears in two ordered pairs. So this single A appears in two ordered pairs with two different elements C, C1 and C2. Well, then using the definition of this as a relation, if ordered pairs are in a composition, that means for A1, C1, there's some B. So A, B1 is in F, and B1, C1 is in G. And using the same reasoning, but with a different intermediate step, if A, C2 is in the composition, that means there's some third element B2, which might be different than the intermediate stage we used for A and C1. So there's some intermediate element B2, so AB2 is in F, and B2C2 is in G. So these colorful underlines are all indicating how we use the fact that this is a composition to tell us more ordered pairs that are in the individual functions. And then we need to use that these are functions. So introducing a third color here. If we look at this first part, this is AB1 and AB2 are in a function. But how functions work is that if you have a single first coordinate, it can only be paired with one second coordinate. So that means these two potential second coordinates actually have to be exactly the same. And going even crazier, that means introducing my fourth color right here. In this case, we have two ordered pairs in G, but because of what we just established, they have the same first coordinate. So really, this is what we are saying. In this orange box, it's really we have two ordered pairs with the same first coordinate. And since we have two ordered pairs with the same first coordinate inside a function, they actually must have the same second coordinate. Okay. And that is actually what we wanted to get to. So I'm going to have to clear all my bright colors. Or before I clear the colors and we have just like kind of a wrap up part, are there questions about this uniqueness proof? So we really are using that F and G are functions, and each of them has a job, takes care of one step in our proof that this is actually a function. So this proves what we wanted because we said, okay, assume we have two ordered pairs in our composition that both have A as a first coordinate, then, so starting from here, we've proved this, which means that A actually can only be paired with one thing. And so that's what really proves, that finishes the proof that this composition is a function. If you start with two relations which are functions and compose them, you get another function. And what we can also say, we wanted to say that this is now a function. What is the output corresponding to input A? Well, that is find the output corresponding to A for F, and then find the output under G corresponding to that input. And we can notice in the existence part, so this first half of our proof here, was that C here is the output that corresponds to A, but what was that? That was G of B and G of B was, or B there was this F of A. So that means A appears in some pair in G of F. The second coordinate is G of F of A. So that means that is what its output is. So this verifies that the way you actually determine the output is input A into F, that's an element of B, input that into G, you get some member of C, and that's the output that you want. Which is good because that's how compositions should work. That's the way we've been thinking about compositions for as long as we've known what compositions are. And so this is how, so we've seen it twice, and this is a kind of common thing that happens. In the existence proof, you often are finding what the output, or you're finding there is an output, but you're also kind of indicating the formula for it. You're indicating, or if you're saying here is the output, we can actually read into that and say, in the process of showing an output existed, we can really identify how we find that output in general. So this proves that if your relations happen to be functions, their composition is also a function. What is actually a more complicated question is, if you have a function f from a to b, then if you take its inverse, which is f is a relation, flip the ordered pairs around, and that's a new relation, that is always a relation from b to a. But when is it a function? When, if you just flip the ordered pairs of f around, do you get a function from b to a? And the answer is not always. So as a couple examples, here are two functions of, or examples of ways that you can flip a function around and it's no longer a function. So in this case, we have our 4 dots representing A, and we have their outputs under the function. If we turn that around, so graphically that means reverse the arrows. The problem is that in the function, we had these 2 points in A going to a single point in B. So when we turn the arrows around, this is a one input in B, which has 2 outputs in A. And that makes it not a function. In the second example, we have another function, but then the issue is there's some B in here, which has nothing going into it. So that means when we turn things around, there's nothing going out of it. And that's another issue with not being a function. Being a function means every input has to have a corresponding output. And here's something in B which is not related to anything in A by this relation. So these are two issues that we have to watch out for. And really making sure that these things don't happen. These things being two things in A go to the same thing in B, so we can't reverse, and something in B not being the output of anything in A. These two properties are actually really important properties of functions, and we'll see that these are the two obstacles we need to overcome. If neither of these things happens, then you're going to have an inverse. That'll take a little bit of work to get to, but these are the two ideas that we want to watch out for. And so we introduce some terminology. Keep in mind this first part is going to correspond to the first example. The second property is going to correspond to the second example. So if we have a function from A to B, we're going to say that f is 1 to 1. And this is a word that you heard before in the context of pre-calculus, but we're going to be, so if you have some intuition, great, but we're going to be developing all the insight and properties that we need. So a function is 1 to 1, sometimes written with the numbers 1 to 1. It's also called injective. It's also called an injection. So this is the adjective, this is the noun version. And these all mean that that first example doesn't happen. So that it is not true that there are two members of A which are different but get sent to the same place. And if you logically analyze this, so the negation comes through, negating an and can be phrased as this if then. Being 1 to 1 means for any elements, any two elements of A, if they are different, they get sent to different places. Or taking the contrapositive of this, if you have two elements sent to the same place, then they must have actually been the same object to start with. So being 1 to 1 is really saying example 1, example 1 doesn't happen. You can't have two different things sent to the same thing. So this is a property we want, so when you try to turn things around, we don't have one object being sent to two different ones. In the second example, we have, or to avoid that situation, is that we'll say that a function f is onto, the fancier word is surjective, or f is a surjection. If for every element of B, there's an element of A which gets sent to it, which is the issue here. There was an element in B which no A was mapped to. So when we turn things around, there's no arrow coming out of that lonely element of B. If we focus on this part here, this is equivalent to saying that B is in the range of F. So for every B, B is in the range, and this can also be phrased as saying that B is a subset of the range of F. So that what we'll really check is that to be onto, you need to say take any element of B, find something which gets sent to it. But a kind of nice way of, or more compact way of saying that is that a function is onto if the range is equal to B. We get half of it for free. The range is always a subset of B, but being onto means you actually get the entire B in the range. And what will also be important is if you have both of these properties. So say that a function f is a 1-to-1 correspondence, said to be a bijective, or say that f is a bijection if it's 1-to-1 and onto. So the conjunction of these properties being one-to-one and onto is going to be an important concept, important enough to get its own name. And if we were to draw a picture of a one-to-one correspondence, what it would look like, we have our two sets here, is that everything is matched up in this one-to-one way. So everything in A is sent to exactly one thing in B. So what's happening here is we're getting this matching up of A and B. So being a function means that every input only goes one output. Being an injection means that if you start in different places, you get sent to different places. Being onto means everything gets used. So if you have a one-to-one correspondence, the idea is you're matching up the things in A exactly with the things in B. So everything is matched, nothing is used twice. So there's exactly one thing on each side of so the lines are exactly pairing things up and everything gets used here. So these three properties are important properties of functions. And before we start really proving things about them, let's see what they look like and how you might show that how a specific function is a bijection, say for instance. How would you show it's one-to-one and onto? So as a first example, if we take the functions from reals to reals, just x squared, that's not one-to-one and it's not onto. So thinking about the negation of those statements, is onto means everything gets used. But there's no real number which outputs -1. And that's what it means to show something isn't onto. You need to find some member of the second set R here, which is not in the range. In this case, we have two different inputs, one and -1, but if you put them both in the function, you get 1 both times. So those are two different inputs which get sent to the same output. And that is what it means to be not one-to-one. One-to-one means if you take different things, you have to be sending them to different places. What we can say though is, if we use this same formula, is say g of x equals x squared, g a function from R to zero to infinity is onto. So the problem is that x squared can't give you negatives, but it can give you everything else. Think about the graph of x squared. So x squared is this parabola. And if you're only looking for outputs from 0 to infinity, you can get everything. Pick how high you want, and there's a point on the graph at that height. What we can also say is that, say, h of x equals x squared, h a function from 0 to infinity to 0 to infinity is 1 to 1. Graphically, what this looks like is saying that we're only looking at this part, this blue part of our graph. And here, different inputs go to different outputs. You can't have this positive and negative giving you the same value. Here, if you pick different x's, they're going to be at different heights. So being 1 to 1 and onto depends in a fairly essential way on the two sets on which your function is defined. What are you taking to be the domain, and what are you allowing in the range? This also, I think, indicates something that you've seen in connection with being 1 to 1 is you talked about the vertical, so the horizontal line test. So what that means, why that helps, or what that has to do with being a 1 to 1 is that if you have a horizontal line which crosses your graph, that is a single output, that is a single height, where two different inputs have that same output. So graphically, being 1 to 1 is saying that a horizontal line intersects your graph more than once. Questions about this example? Okay. So the next example is going to be more positive in that we're actually going to show, and actually carefully show, not graphically or anything, that the function we define really is a bijection, that it's both 1 to 1 and onto. So let's define g from R to R being 2x cubed plus 1. We're going to show that this is a bijection. So that means two things. First, show that it's 1 to 1, and then show that it's onto. And the moves in here will be sort of familiar from when you've been talking, when you talked about inverses, whenever you talked about inverses. But we want to be aware of what the purpose of all the moves are. So first up, we want to prove that it's 1 to 1. So being 1 to 1 means different inputs go to different outputs. Often the better way of writing a proof is the contrapositive, which says assume the outputs are the same and then prove that the inputs are the same. Why that's better is if you know that two things are equal, if they're the same, then that gives you an equation, and equations are easier to work with than saying these two things are different, saying they're not equal. If things are equal, then we can do the same thing to both sides of the equation and get another equation. So how being 1 to 1 will start is always take two elements of the domain and assume their outputs are equal. Then where we want to get to is we want to get to that the x and y you started with, these two inputs that had the same output, those are actually equal to each other. And so this is proving the only way to have the same output is if you were actually starting from the same place. So how does this go? Well, g is given by a formula. So that means for the x and y we started with, 2x cubed plus 1 is equal to 2y plus 1. But now, keeping in mind where we want to get to and sort of letting your algebra instincts take over is, well, let's start canceling. Subtract 1 from both sides to get 2x cubed equals 2y cubed. Divide by 2 on both sides. That gives us that x cubed equals y cubed. And then we can take a cube root, which means that x equals y. And that means if you have the same output, you had to have the same input, and that means that a function is one-to-one. This fact here is, so we can describe it as saying take the cube root of both sides. We can also think of it as saying that x cubed is one-to-one, meaning you have two numbers x and y, so they give you the same output under x cubed, then they had to be the same input. And running the same kind of argument, if x cubed and y cubed are equal, we can subtract 1 over, factor as a sum of, as a difference of cubes, and we get two cases where x and y both have to be equal to each other. So this would be enough. A lot of, so the basic algebra rules about adding 1, dividing by 2, taking cube roots, we're still allowed to use those. But they can all sort of be rephrased in saying that certain functions are one-to-one. Questions about this proof? And again, really focusing on this part. Okay. So then what does it look like to see that something is onto? So being onto means that given an element of the real numbers, really talking about taking something from the output space, we need to find some input. So if you put that into a function, you get this y out. So given a real number, we need to show that it is the output for some appropriate input. So if this is what we want, then using the formula f, or sorry, I used the wrong letter in here. So this shouldn't be f, this should be g, and all these are g's. But what we really want to use is that this function g had a formula. G was 2x cubed plus 1. So we want to find some number x0. The 0 here just to specify not being a variable. This is a specific number we're talking about. We want to find an x0, so if we put that into the function, so if we cube it, multiply by 2, add 1, we get this y back that we started with. And if you solve this equation for x0, this is the number that you get. And this number, if you put it into the function, is going to output your y. So to see why it works is what's going to happen is this is specifically designed so you get these pairs of canceling pieces, leaving you with just y. So if you put this into your function, so g of x0 is g of this cube root of y minus 1 over 2, and g had a formula that was 2x cubed plus 1, so we put that in for x. And now what we see is all of these pieces canceling. The cube and the cube root cancel. 2 times y minus 1 divided by 2, the 2's cancel. Y minus 1 plus 1, these 1's cancel and they give us just y. So what this means is that here is a number, so if you put it in, you get y out, and y was anything. So that means that this function is onto. No matter what real number you want, that is the output of some input. Questions about this proof here? Okay. So these examples are really how you show something is onto and one-to-one, or not onto and not one-to-one. Proofs that you're one-to-one and onto will look really similar to this. Assume that you have two things with the same output and prove that those are equal. If you have a formula, that really means solving the equation. If your function isn't given by a formula, there might be different looking work, but you still need to get to saying the inputs are the same. Showing that you're onto is always looking like pick something from the output space and find an input which is sent by the function to that y you started with. And when it's an equation, it's going to be, or when your function is given by a formula, set up an equation and solve it, and then check that if you put this into your function, things cancel, so you output the y that you wanted to show was some output. This first example is really showing if you want to show you're not one-to-one or not onto. They're really counterexamples, existential statements. Show there's a number which isn't an output, or show there are two inputs which get sent to the same place. So besides looking at specific examples, we'll also want to establish some properties. Important bunch of properties are, if you have two functions and you know that they are injective, surjective, or bijective, what can you say about their composition? And what happens is that if your two functions have one of these properties, then the composition also has that property. D here tries to reverse that. If you have your composition is a bijection, then the first function is injective and the second function is surjective. So to prove this, we want to keep in mind, what does it take to prove something is injective? It means if you have two inputs sent to the same place, those are equal. Surjective means you have to find, so G composed with F goes from A to C. Surjective will mean for every C, there is something in A that the composition sends to you. And how we execute those proofs is we're going to have to use that we know the two individual functions are injective, or we know the individual functions are surjective. So this theorem is a good combination of, first, how do you prove something has these properties, but also how do you use the fact that functions have these properties. So here's one more example that I'll skip over for now. So what do these proofs look like? So part A is saying that if you have two injections and compose them, you get another injection. So there are really two ways to do this. We have two phrasings of a function being injective. That means different inputs get sent to different outputs, or the same input, or if you have the same output, it came from the same input. I proved it one way, assuming different inputs go to different outputs, but it would be worth trying to come up with a proof that uses the other version also. So for this version, we're saying G composed with F goes from A to C. So we want to start with saying that take two elements in A and assume they're different. What we want to prove is that the composition sends them to different places. And no matter what happens on the inside, that's what a proof of something injective has to look like. Different inputs go to different outputs, or the same input must have come from the same output. And in the middle, we're going to have to use that we have two injective functions. And what can help, which isn't what, so this isn't a proof, but it can help, is drawing some pictures, A, B, C, and we're saying we have two elements in A, and we have function F and a function G. And part of these proofs is thinking, well, what can I even do? And a good place to start is, well, you have two things in A, and you have a function which sends things into B. So what happens if you apply that function to the two objects you started with? Well, since F is injective, and that's a property that we're assuming, so we want to use it somehow. Since F is injective and we're starting with two different elements, F and X and F of Y are also different, and they are, I think this got cut off here. These are elements of B. So graphically, that's saying that these two X and Y we started with get sent over to F of X and F of Y in B. But then we're in kind of the same situation. We have two things in B. We have this function which takes us from B to C. So what happens if we apply that? And again, since G is injective and we have two elements which are not equal, their images under the function where they get sent to is also not equal. And that's really where we wanted to go, because if you take X, apply F, and then G, that is what you get when you apply the composition. And if you take Y, apply F, and apply G, that is what you get when you apply the composition. So this is where we really wanted to get to. If you take two distinct non-equal elements of A, the composition sends them to different places in C. And you know that because you reused that the composition is a two-step process. You stayed different when F sent you into B, and you also stayed different when G sent you into C. So we'll finish the rest of this proof next time, but in all these pieces, how we proceed is the composition is talking about the whole step from A to C. The individual functions go from A to B and B to C. So the way you prove something about the composition is you check that you can do it through both steps. Right, so we'll finish this proof up next time. If you have questions, I can definitely stick around. If not, there is a homework assignment that's due by tonight. Um, but as really with all of the assignments, I would rather have you turn something in a little late than turn in something half done. The point of the homework is to give you practice working on these problems, and uh, I care more about you putting in enough time to practice than the due date that I've set. So make sure that you, or try to get that turned in tonight. If you need extra time, just let me know.